start from somewhere. Let's quickly start from the main points I want us to study. Yeah. So you can as well read the foundational part yourself. So let's look at charged particle in a magnetic field. Now pay attention that when a charged particle is moving through a magnetic field, that is, I have a charged particle Q is moving in a magnetic field. How do we calculate the force on it, and how do we find the direction of the force? See, whenever we have charged particle in a magnetic field, what do? We use this force. That is, force will be exerted on the charged particle, and that force equals to what? QVB sine theta. You see, this is what we use to find the force on a charged particle in a magnetic field. Q is the magnitude of the charge, V is the velocity, B is the magnetic field. The unit of this is Tesla. Yes, Tesla. Or you say magnetic flux density, Weber per meter squared, whichever way. And theta is the angle. Now you observe that when your theta is 0, you observe that what this force will be equal to 0. That is, this where your force will be 0. But if your theta is 90 degrees, you observe that your force will be maximum. Yes, your force will be maximum when theta is 90 degrees. And when theta is 90 degrees, what do we see? Now pay attention. We say the force is maximum when the charge moves in a direction that is perpendicular to the magnetic field. Are we together?
Yes.
That is, when this charge moves, that is, let me say this is the direction of the charge now. This is where the charge is moving to with this velocity. And let me say the magnetic field is something like this. So you observe that well, this and this are perpendicular. So when you have this case whereby you can have different other case too. But if the charge moves in a direction that is perpendicular to the magnetic field, we say that theta is 90 degrees and the force is maximum. All right. But what happens when the charge moves in the same direction as the magnetic field? You observe that at this point they are parallel. Theta is 0, and from here your force will be what? 0. The force between them will be 0. Exactly. I believe you are getting it.
Yes.
Are you getting it?
Yes, sir.
I can't hear you.
Yes, I'm getting it.
All right. So what is now the direction of the force? Now pay attention to me. To find the direction of the force, we use the right hand rule. What do we use? The right hand rule. We use the right hand rule to find the direction of the force. To find the magnitude, we use this. Then to find the direction, we use the right hand rule. Now pay attention. To find the direction of the force on the moving charge, we use the right hand rule. How do we use the right hand rule? Now pay attention. Let me help you draw the right hand. Just help me manage my diagram. Let me just draw the right hand. This is the longest. Followed by this. And followed by this one. Now, see the right hand now. Good. This is your right hand. Pay attention to it. You observe that, you see, this is your thumb. And look at all these fingers. These are your fingers. These are your fingers. And what you see here is your palm. You see this palm represent the force. Are we together?
Yes.
This thumb represent the velocity. And this finger represent the magnetic field. That's it. It means that if you can position your hand in a way that the thumb will travel in the direction of velocity, the magnetic field, your fingers will travel in the direction of the magnetic field, and you are now observe that wherever your palm is facing, this will be the direction of the what? Of the force of them. Now, let us take an example on this. Let's take, for instance, that I'm having something like this. I have a positive charge like this. Pay attention to it. I have a positive charge moving in this, check. This is the direction of the magnetic field. Now check, this side is the positive charge is moving in upward direction. And I ask you that, oh, what would be the direction of the force? Now pay attention. Let me share my video so you observe the way I'm going to position my hand. How do we share this? Let me switch on the light. Can you see me now?
Yes.
All right. Now observe. So you can see the board and me at the same time.
Yes.
Okay, good. Now pay attention to something. See, I want to know the direction of the force. How do I do it? Now, look at where I'm going to position it to. Look at it. Don't forget, this my thumb will show the direction of the velocity, and this is the velocity v. See, my thumb will show the direction. So my thumb must be upward, whether this or this. Just make sure that what this your thumb is facing upward. Now, your fingers, check. This your fingers that you have here must point in the direction of the magnetic field. Then check, look at where I'm positioning it now. You observe. If I position it this way, I'll be wrong. See where the magnetic field is facing, see where my finger is facing. So I have to position it this way. Now, if you do this, you observe that the force is going into the page. Yes or yes? Check.
Yes.
Exactly. Or is going away from me. That I'm the observer. Are we together?
Yes.
Is it clear?
Yes. Yes.
So the force here, F, is going what? Into the page. The force is going to the page. Now, assuming that what you are having here is not a positive charge, is a negative charge, no problem. Assume you have a positive charge. Whatever direction you get, reverse it. This one now is for positive charge. Position your hand the way you position positive charge. This is the velocity. This is the velocity. This is the magnetic field. And the force, your palm will show you what? The force. Now, the force is going into the page. If it is a negative charge, what do you say is coming out of the page? Out together?
Yeah.
And out together?
Yes. Yes.
Exactly, it's clear. Good. Okay. Let's look at another one. Assume that you're having something like this. Look at it in blue here. And then you have a positive charge like this going downward. And this is your magnetic field. Now, what would be the direction of the force? Now, let's position our hand. Let's position our hand. Don't forget, your thumb is your what? Is the direction of velocity. So, anyhow you are positioning your hand, endeavor that this thumb is downward. Now, let's go. Check it out. This one is facing down. And don't forget, this direction like this is not right. The magnetic field moves this way, so your finger should follow that direction. Are we together?
Yeah.
Then you observe. Hello, are we together?
Yes.
If you observe, hello, are you following?
Yes, sir.
Good. So you observe this one is coming downward, this is going this way. So therefore, if you observe, the force is coming out of the page. Are we together? Yeah, the force is coming what? Out of the page. Exactly. The force is coming what? Out of, or if you do your hand, you can. What is it?
What do you mean by out of the page?
Out of the page, check. Position your hand. Okay, look at this screen as your page. Or look at your screen as your page. Like, look at your screen, your phone screen as your page. Position your hand. You see that your hand, you see, if your hand is moving away from you, that's into the page. Like, the page is like, consider like you're having a screen in front of you. Are we together?
Yes.
Yes, and position your hand, you see.
Okay.
So that's that for that. Are we together?
Yeah.
Okay, what of if you are given something like this? Check this one out. This one is a little bit trickier. Look at something like this. You have this one, like you have something like this. So this is your magnetic field. And look at this one. You have a positive charge moving in this direction. Coming, you have something like this. I'm coming. Let me use another color for this. Now look at where this is moving. Check it out. Now, how do we find the direction of the force? Now, if you observe this velocity now, look at the way we are having it. It's having some angle theta. So what you are going to do is that you break it into components. Remember, if I break it into components, the horizontal component will be pointing in this direction, and the vertical component will be pointing in the downward direction. So we choose them one after the other. So if you observe, if you are choosing this one, you observe that this one and this one here, this velocity and this magnetic field will be like parallel to each other, or you can say anti-parallel, but let me just say parallel to each other. And remember, if they are parallel to each other, this is parallel, the force is zero. Are we together? Yeah. Hello?
Yes.
Yeah, the force is zero. So therefore, you can't even choose this component. Now, I think that is this component you are going to choose. Now, observe. The magnetic field is going in the right direction. So place your hand in a way that your finger will face the right direction. And don't forget, your velocity, that one is going downward. So what do? You are going to what? Position your hand downward. All together? Exactly. So where's the force going to? Out. It's going outward. All together?
Yes.
That is, it's coming towards you. Do you observe that?
Yes.
It's coming towards you. So the force is coming out of the page. Now, there are some times that you will see some notation like this. You see notations like this. Let me write it here. Means that the magnetic field is going into the page. And if you see a dot like this, it means that it's coming out of the page. There's a reason for this signs, but don't worry about that. If you have an arrow, hello, are we together? If you have an arrow, are we together? Remember that this is an arrow, yes or yes?
Yes.
If you view an arrow going away from you, you'll be seeing this end like a cross. Imagine that an arrow is going away from you, you'll be seeing this end and you'll be seeing cross. It means that it's going away from you, that's into the page, it's going away. But if they are pointing arrow at you, you will only see this dotted mouth. And that's why they are using cross and dot. So this is going out of the page. Out of the page. Good. So let us look at an example of that. Okay, let me say that you have a case whereby you have the magnetic field to be this way. If you see this cross, take note of what it means. Okay? This is your magnetic field. And then if you observe, this is your velocity. You have a negative charge moving in this direction. Now it's a negative charge now. Now, what will be the direction of the force? Firstly, assume you have a positive charge and let's determine the direction. Don't forget, your finger represents the magnetic field. So this cross shows that your finger is going into the page like this. So you are putting it this way. All together?
Yes.
And look at your finger. It's pointing in the direction of the velocity, northward. I mean, upward, right?
Yes.
So if you observe, the force on this charge will be going on the left. But because it is a negative charge, I will reverse the direction, then it's going to the right. All together?
Yes.
Exactly. That's how to do it. So that's that about that on that. So as simple as that. Okay? So that's that for that. All right. Let's move. Next. We want to look at magnetic force on a current carrying conductor. So we are going to solve more questions on the group. Magnetic force on
Sir,
yes.
how will questions be set on that right hand rule?
Okay, you have question. Okay, I can hear you.
No, like I said, how will questions be set on it? Because it's not very clear.
Okay, they give you guys question on it. Do you have them
I'm
with
just
you now?
No, I'm just asking that how will questions be set on it?
Don't worry,
Because it's
maybe I
not
solve a
very
question on the
clear.
group, you will see them. Are you there?
Yes.
Okay, let's go. Magnetic force on a current carrying conductor. Now pay attention. You see, let me tell you something that there's an experiment performed by Ørsted. You can read more about that experiment. That, in a nutshell, it is to show that a current carrying conductor creates a magnetic field around it. Don't forget that statement. A current carrying conductor creates what? A magnetic field around it. Are we together?
Yeah.
Good. And how do we find the magnitude of the force on the current carrying conductor? Now pay attention. Remember that we have this formula before. F equal QVB sine theta. That is recall. Are we together?
Yeah.
Are we together?
Yes.
Okay. Let us do something. Let's do something like this. Divide this by C and multiply by T. Remember, I've not done anything by cancel out this T. Yes or yes?
Yes.
And remember that current is equals to charge divided by time.
Okay.
And remember that velocity times time will give us distance, which will be the length of the conductor. Therefore, I have a formula which is F equal ILB sine theta. But me, I love to use it this way. BRL sine theta. All of them are the same. BRL sine theta. Or you say ILB sine theta. This is how to find the force on a current carrying conductor. Now, pay attention to something. This is how to find the magnetic force on a current carrying conductor. Now, there are some things that you can be asked under this. Now, consider that you are having a current carrying conductor this way. Let's say this is the word, this is the conductor. And the current is moving in this direction. This is the electric current moving in this direction. Don't forget I told you something that what? A current carrying conductor creates a magnetic field around it, creates a circular magnetic field around it. Now, how do we know the direction of this magnetic field? That's what you want to learn now. Now, pay attention to it. I will still share my screen once more. I'll still share my screen once more. There are some questions that you can be asked to calculate. After you calculate, you also get the direction again. So you'll be solving and you'll be asked to find the direction. Now, let me share my screen again. Okay. Can you see me?
No.
Sorry. What about now?
Yeah.
Okay. Now, hold on. Look at this. See, you want to know the direction of the magnetic field around this current carrying conductor. So this is what you do. It's also right-hand rule you are using here, but in another form. That is, you are going to, this one, you want to know the direction of the magnetic field. Magnetic field. Now, don't forget that assume this is a conductor, it's carrying electric current. It creates a magnetic field around it. So how do you calculate the direction of that magnetic field? Will it be clockwise or counterclockwise? Now, grasp your conductor in a way that your thumb will point in the direction of the electric current. That is, this will be your thumb. Are we together?
Yes.
Then this will be your other finger. Are we together?
Mm-hmm.
Exactly. Exactly. So then let your thumb point in this direction of the current. Therefore, your magnetic field, if you observe, how will it point? Maybe I'm not drawing my diagram very well. Mind my diagram. Don't mind my diagram, please. So let your thumb go in this direction. Let your thumb go in this direction. So what do you observe? You observe that now, check. My own is going this way, counterclockwise. Are we together? It's going this way, counterclockwise, like this. This is the direction of the magnetic field. Now, what do you observe? Pay attention. Let me draw it here again. This is a current carrying conductor, and this is the electric current. Now, the current is going this way. If I grasp my conductor so that my thumb points in the direction of the electric current, you observe that magnetic field will be going in this direction, which is like counterclockwise. So it means that it will be something like this, counterclockwise. That is like this, like this. Altogether, if you observe at the left-hand side, which is this part, at the left-hand side, which is this part, the magnetic field is coming outward. Are we together?
Yes.
So it means that on this part, your magnetic field is like a dot. Are we together? Why at the right-hand side is going inward, which means your magnetic field here is what? A cross. Are we together?
Yeah.
So it means that if I'm telling you that, okay, let's assume a cardinal point now. This is our east, this is our west. So at the east position, you observe that the magnetic field is going outward. In the west position, it's going here, inward. If I check this upper part, you know that it's going this way, which is what? To the left. Coming here, it's going which way? To the right. And that's how it will be going, that direction of the magnetic field. So we use the right hand rule. This is gotten using the what? The right hand, let me say the right hand grip rule. Because it explains that you'll be gripping a wire. And that's that for that. Are we together?
Yes.
Okay, good. So, and what is this theta? Let's continue. What is this theta? Well, theta is just the angle between the direction of the electric current and the magnetic field. Now, pay attention. If I have the electric current, the current carrying conductor this way, this direction of the current, and the magnetic field is moving this way. So you observe this theta is the one we are referring to here. That the theta, that is the angle between the direction of the electric current and the magnetic field. Yeah. So that's that on that. That's that on that. So we are concluded this part. Can we move on? And the last one I'm discussing on before don't worry, this video will be on YouTube. I'll send to YouTube, and also I will post the link of the video you are going to watch. I'll post the link there. So when I post it, now let's look at the next thing we want to look at. Let's put it on the next page. That's talk on a current loop. Talk on a current loop. Remember, if I'm talking about torque, I'm talking about turning moments. And if you look at a loop could be a rectangular loop or a circular loop, something that can at least rotate. Okay, pay attention to something. Let's consider a loop, a rectangular loop. And let me consider it to be something like this. Looking at the left-hand side of the loop, observe this loop here. Calling. Okay. Look at this. So, from here to here, we have to be the width of the loop. And here is the length of the loop. And the current moves in this direction. You have the electric current moving in this direction, I. Going in this direction, I. All right. If you observe, At this part, at the left-hand side of the loop, the current is coming outward. Don't forget, outward, I use this direction, this dot, to tell you that. While on the right-hand side of the loop, I'm having the current moving inward. All together?
Yes.
Okay. All right. Now, from here to here correspond to the width. Here to here correspond to the width of the rectangular loop. So let me call this the center. Let me call from here to here is the width of the loop. This is the width of the loop. Okay. Okay, now. I'm coming, please. Okay. Now I want to ask a question real quick. Now the question is this: what will be the direction of the force here, and what will be the direction of the force here? How do we get direction of the force? How do we get direction of the force? We have the current moving that way. Okay, and observe, you have a magnetic field like this direction. Now I will use my right hand rule. Okay, so look at the way the charge is moving like this. So let your thumb be like, I'm coming. Let me help you position my hand. Then I'll tell you how to position. Now, position your hand in a way that your fingers will go in the right direction. That all your four fingers, except the thumb, will be going in the right direction. Position that. All together?
Yes.
Position. Let me show you what I'm saying. Hey, sorry. Can you see me?
Yes.
Okay, now pay attention. I want to look at the direction of the force on this loop. Okay, see. Check something out. I want to see my magnetic field is going in the right direction, and my fingers must go to the right. These four fingers must go to the right. Now, don't forget that what? Look at the way the current is. Look at the current. This part shows that what is coming outward. Just like that's how the charge is moving. It's moving outward. So my thumb must come outward this way. Why this finger must show us direction of the magnetic field? If you observe here, your force will be going upward. Therefore, the force on this part is upward. F is upward. This is your force. Now, let's look at this part again. Magnetic field is going this part. And here, your current is going inward. So your thumb must go inward. If you observe, the force here is going down. And what do we call this in physics? This is a couple. It means that what? There will be a turning effect on this loop. Are we together?
Yes.
Exactly. There will be a turning effect on that what? On that loop. Exactly. That's what I wanted to show you. Good. So after showing you that, let's move on. Okay. What do we now say? To find the torque will be equal to what's the formula to find torque? Moment. Force times perpendicular distance, right?
Mm-hmm.
Exactly. Force and perpendicular. So one of the force times perpendicular distance, and that is it. Okay, don't forget. How do we find force? We say ILB sine theta. Then we have this times W width. And torque equals to what? I. You see, don't forget. Let me say B. Length times width will give me what? Area, right?
Yes.
BAI, this for the current, then sine theta. Now pay attention. If I have multiple coils or loop, for a multiple coil or loop, my torque will be equal to. Now, For multiple chord, let me say I have like n number of loops now. I'm taking like one as an explanation here. What if I have 10 loops, 15 loops, 20 loops? Then I'll not take to what B-A-N-I, Bani. That's Bani sine theta. Are we together?
Yes.
Exactly.
So the n represents the number of loops.
Yes, exactly. So your theta is the in fact, let me even tell you, it could have generalized a situation for you whereby what if you have something like this? Whereby we now have like check something out. So we have something like this theta. Now check. You see that the theta is the angle between the direction of the magnetic field and the what? And the perpendicular line to the plane of the loop. Look at this, the perpendicular line. So this is the angle between, that theta is the what? Is the angle between the direction of magnetic field and the perpendicular line to the plane of the loop. To the plane of the loop. And that is it. Okay, let's move on. Take note of that there's a particular terminology we call magnetic moment. You see, there's something we call mu, and that's called magnetic moment. What's magnetic moment? Magnetic moment is equal to NIA. Is equal to NIA, number of turns times current times area. So if I replace NIA in this formula, with magnetic moment, therefore my torque will be equal to what? My torque will be equal to what? Mu what? Mu B sine theta. So just look at it. This magnetic moment. So if I replace it here, I'll have mu B sine theta. Do you see that?
Yeah.
Exactly. So now what remains for you to learn is Ampere's law. After Ampere's law, you learn Ampere's law in fact different in different cases. Then I'll teach you Biot Savart law just in case. And what again? Ampere's law basically. But you learn Ampere's law in a current carrying conductor, a straight conductor, a solenoid, and a toroid. So everything is what it has been done on the level. But before we go, there are sometimes that two conductors will be placed beside each other. I wish that go and study all this. I want us to solve the question live instead of on the group. Okay?
Yes.
So I will have compiled questions. I'll compile questions, please. So take note that if the current is going in the same direction, there will be a force of attraction between them. Take note. Attractive force, yes. Attractive force if the current is traveling in the same direction. Repulsive force in opposite direction. Now take note of something that they are both current carrying conductor. Yes, they are both current carrying conductor. And don't forget, let me consider this conductor now. Remember, as it's carrying current, magnetic field will be going around it. Now, let me tell you, if they ask you to find the force on this, the force on conductor 1, what do we see? Pay attention. That you can be asked to find the force on this conductor. And take note that what? The force on this conductor can be due to the magnetic field created by this second conductor. That is this magnetic field B2. Altogether, this magnetic field B2 created by this conductor who have effects on this force. So how do we calculate force 1? You will see F1 will be equal to, remember, BIL. Have you now? So what type of B will you use? You will use B2. B2, I1, L1. Please don't forget this thing. Because that force is as a result of the magnetic field created by the second conductor. So B2IL sine theta. But the thing is that what is B2? From Ampere's law, you will learn this thing from Ampere's law. You will learn this thing from Ampere's law. Don't worry, I will attach the link of the video to this particular video on YouTube. So from Ampere's law, so B2 or magnetic field is mu naught I over 2 pi r. This r is the particular distance where you want to find the magnet. It can be a point here. So that's the distance. So this mu naught I2 over 2 pi r. So this is when you're having two conductors placed beside each other. So let's go. So if they give you a question, you observe. Don't worry, you are solving many questions. So let's go. What's my B2? Mu naught I2 over 2 pi r. Then I have I1, N1. All together.
Yeah.
So how do we now find the force F1? Therefore, the force F1 will be equal to mu naught I1 I2 all over 2 pi r. Please keep this formula somewhere. So you should know that whenever they are telling you that two conductors are placed beside each other, mu naught I1 I2 L. There's a length here, the length of the conductor, and that's all. So all right. So practice all these things.
So is your left hand rule?
What is it?
Is your left hand rule?
Yes, now. Very well. But we have not actually considered, whatever we have considered here is basically on right hand rule. There's actually a left hand rule, but that is under what? Electromagnetism. Are we together?
Yeah.
Let me tell you that. Let me see now that you have, let me say, a particular conductor in a magnetic field, and you want to know the direction of the conductor will move. So they'll be telling you left hand rule that you'll be positioning your hand this way. But this right hand is sufficient for most of this question. And take note of where we are using them. If you have a charge moving in an electric field, you want to know the charge moving in a magnetic field, you want to know the direction of the force, right hand rule. Using this your palm. Force, velocity, magnetic field. That's for that. But a conductor carrying electric current, you want to know the direction of magnetic field, you'll be grip rule, or here Maxwell corkscrew rule. Using this. And that's for that.
So that is the left hand rule now.
What is it?
So that one is not necessary.